Hello students, today we will discuss about particle in a box, how to obtain the Schrodinger wave equation for a particle in a box, and how do you analyze the energy of a particle using Schrodinger wave equation. So for that we are considering a particle is in a well or in a box in which it is free to move. So if a particle is free, then the potential experienced by the particle will be zero. Since it is confined to be inside the box, we can see that towards the boundary, at the boundary and beyond the boundary, it will be experiencing high potential, which means the particle is not allowed to go into the beyond the boundary. It is confined up to the boundary. Similar to the right hand side also, we can see the potential is very high, so that the particle cannot jump over the barrier. So this is what we have mentioned in terms of one direction. Similarly in x direction, as well as that is in the width as well as in the height direction, you can expect such a potential. So for the time being, we'll be considering a one-dimensional motion, one-dimensional case, and it will extend into the three-dimension. So we are considering a particle of mass m and energy E confined in a cubical potential box, and the side of the box is given as L. So we can consider that it is free to move between 0 and L in x direction, similarly between 0 and L in the y direction, and between 0 and L in the z direction, because we are considering a cubical box. So the potential inside the box is 0 as the particle is free to move. It will not experience any potential, that is nothing to block or delay or confine them. Nothing is hindering them to have a free motion. Okay. While at the boundary, you can see there is a steep rise in potential to infinite value everywhere outside the box. So therefore the particle will be rebounding. Whenever the particle strikes on the boundary, it will be rebounding. So let us consider the particle. As the particle cannot exist outside the box, what would be the wave function in these regions? Yeah, what do you mean by wave function? It is the representation of the de Broglie wavelength associated with the particle. And where would we get a wave, de Broglie wave? Yeah, de Broglie wave would be found wherever the particle is. So will there be a wave outside the box? Is there any possibility for that? No. Why? Because the particle is inside the box. So we can expect a wave only inside the box concerned. So the wave function outside the box will be 0, and we can have a non-zero value for wave function only inside the box. So let us set up Schrodinger wave equation for the free particle in the box. We have seen that it is given by del square psi plus 2me by h cut square psi is equal to 0. And instead of del, that is Laplacian operator del square, we can express in terms of x, y and z as dou square by dou x square of psi plus dou square by dou y square of psi plus dou square by dou z square of psi plus 2me by h cut square psi is equal to 0. So we can consider this wave function. We have mentioned that we are considering a particle with dimensions in all the directions, that is x, y and z. So let us split up the wave function as product of x, y and z, where the capital letters implies it is a part of the wave function which depends only on x direction, and y is the particle of the wave function of the particle along the y direction along, and capital Z is depend upon the direction set. Okay, so then the equation 1 could be rewritten by substituting with psi. You can split up. So what you get, let us write it. So dou square by dou x square. So in that case, x is the varying function, and the only wave function depending upon x is capital X, and other y and z are constant. So for the first term, you'll have capital Y, capital Z as constants, and the remaining is dou square by dou x square of x. Plus, similarly for the second term, it would be capital X and capital Z are constant since we have a variation with respect to y alone. So the wave function could be written as dou square capital Y by dou y square, plus yz, capital Y, capital Z, which are the wave functions in y and z direction, into dou square z by dou z square. Here I think it has to be x. Okay, plus 2me by h cut square into psi. So instead of psi, we are going to write x, y, z equal 0 as given by the first equation. So now you can see that we are going to divide it throughout by x, y, z. So what you get? So if I divide it by x, y, z throughout the equation, we can see that y and z will cancel off in the first term. So remaining is only 1 by x, plus similarly x and z will cancel off, remaining is 1 by y, plus y and x will cancel off, remaining is z. So 1 by z, dou square psi by dou z square, plus 2me by h square, and x, y, z has completely cancelled, which is equal to 0. Now we'll be taking the x term along in the left hand side, and all other terms are brought to the right hand side. So here you can see that left term is depending only on x, while rightward term is independent of x. Okay, so we have something as a function in one LHS is equal to a function which is not equal to x, and they are actually equal also. Okay, so how that is possible? This is possible only if these are equal to a constant. Constant aanengil matramana such a relation is possible. What kind of a relation? That is, a function can be equal to another function which is independent of x. That is possible only if the value is a constant. Numerical aayittulla value aanengil mathramayirikkum we will be able to equate it. Okay, so in that case, we can see that LHS is a function of x and RHS is independent of x. So correspondingly, you can write it as each side must be equal to a constant, and we consider that constant as minus kx square. Minus is given so that you'll get a expression of this form. Okay, so instead of the entire term, we are considering it as minus kx square. So minus k square, when it comes to the LHS, it becomes plus kx square equal to 0. So the right hand side is also equated. What is right hand side? That is minus 1 by y dou square psi by dou y square, minus 1 by z dou square psi by dou z square, minus 2me by h cut square equals minus kx square. Okay, so similarly what we have done, we will consider only y term alone in the LHS, and remaining things will be taken to the RHS. So again you get an expression of the form y function alone in the LHS and independent of y function in the RHS. So considering the same argument, you can equate to a constant. Since it is a constant for the y function, we denote it as minus ky square. Okay, and so again this can be equated to the constant. So considering this part alone, you can see that we'll again take my 1 by z dou square psi by dou z square alone in the LHS, and remaining constants are taken to the RHS. So here also you can see that LHS is function of z while RHS is not a function of z, which can be equal only if it is both are equal to a constant, and constant is given by minus kz square. So finally what you have is, from this relation, what you have is kx square is there plus ky square plus kz square will be equal to 2me by h cut square. Okay, so here I think minus is also there, just missed it out. Okay, so what you have is an equation of this form. So the general solution of this equation is given by capital X equals, that is the general solution of this equation is given by capital X can be a sine wave or a cos wave. So you will take a combination of those two. So X is equal to A sine kxx plus B cos kxs. That is a wave with an amplitude B moving in the direction k with a wave vector k and direction x. Similarly, it could be a sine wave also with an amplitude A moving in the x direction. Okay, which is the solution for this equation. So here you can see that considering the general equation, A and B has to be found out, isn't it? We are not aware of what is the value of A and B. So for that, we make use of the boundary conditions and normalization condition. So let us first take the boundary condition. So what is a boundary condition? Yeah, boundary condition is there is no wave function at x equal to 0, that is one border, and at x equal to L, which is the other border. That means we have a box with x equal to 0 over here, and that is the starting point of the box, and the other is given by the end of the box, which is again given by L. Okay, so at the boundary, the wave function is equal to 0. So considering that, you can write it as giving x equal to 0 in this equation. What is sine 0? Sine 0 is 0. So A sine 0 plus B cos 0. Cos 0 is 1. So we have B along from the RHS. And what is capital X? Capital X is also 0. We have already mentioned it. There is no wave function at the boundary or beyond the boundary. So capital X is also 0. So from this we can see that the value of B is equal to 0, and substituting back into the main equation, you get capital X as just as A sine kx. Okay, now we need to find out what is A. So we have eliminated one of them, we have determined one of them. Now we need to determine what is A. For that we consider the other boundary, that is x equal to L. So at x equal to L, you can see that A sine kxl is also equal to 0. That is what we mentioned. At the boundary, wave function is 0. Okay, so if a sine term, sine of something is 0, A cannot be 0. Why? A is the amplitude. Amplitude illande namukku existence illa, left wave function pinne oru meaning illa. So A must be non-zero value. So the only possibility is that the sine kxl can be 0. So when would a sine kx, sine some factor is 0? Yeah, only if that factor is 0 or pi or 2 pi or 3 pi, etc. Or in general, I can write whenever kxl, which is the factor of sine, is equal to n times pi, I have given a suffix x in order to indicate that it is the integer related to kx dimension. So whenever the kl is equal to n pi, I will get a 0 value for sine, and correspondingly this equation will halt. Okay, so from this relation I can write what is kx. So what is kx? It is just n pi by L, where n is just an integer. So we can substitute now x as A sine nx pi by L into x. So still we have not determined A, which is the amplitude. For that, we will consider the normalization condition. So what is the normalization condition? Yes, we have studied that there is a probability for finding the particle anywhere in the space, isn't it? And what is the condition over here? It is not anywhere in the space, it is actually confined in the space in a box. So what is the integrating limit here? Yeah, it is from 0 to L. Instead of minus infinity to plus infinity, we'll have the probability for finding the particle only within the box, and it is limited by the value of x as 0 and L. So instead of minus infinity and plus infinity, you have 0 and L as the limits. Now you can substitute for psi star. What is psi star? A sine nx pi by L x in their conjugate, that is star is given. Then psi as such, which is A sine nx pi by L into x of x. This is the whole thing. Okay, sine of this thing. Okay, dx equal to 1. Now we can see that A star is A itself, and so we can take out A square out. It is A is a real number, so integral 0 to L sine square, sine star and sine is there, so we have it as sine square nx pi by L into x dx. Now you can express sine square in terms of cos as, what is sine square? Something is 1 minus cos 2 of that factor divided by whole divided by 2. Okay, make use of the mathematical relation, trigonometric relation. So sine square something is 1 minus cos 2 of that something divided by 2. So now it is easier to integrate. So if you integrate, you can say that it is a square, 2 is a constant, we have taken it out. And what is the integral of 1? We are integrating with respect to x. So integral of 1 is x minus, what is the integral of cos? Cos is sine. So we have sine 2 nx pi by L into x. So in the integration we'll be dividing it with the constant. Which are the constants of x? Coefficient of x is given by this much. So we'll divide it by 1 divided by 2 nx pi by L. So L will come in the numerator. And we are putting the limit 0 to L. Now if you apply the limits, you can see that by giving the maximum limit as L, you'll get it as L minus sine 2 nx pi by L into L. So L and L will cancel off, so remaining is n pi. So what is sine of n pi? Sine of n pi is 0, so that term will be 0 minus, now applying the lower limit, you get x is 0, 0 minus sine 2 nx pi by L. Okay, so into 0, so that is sine 0. Okay, so applying 0. So here what I have shown is that I have taken the first x value and applied the maximum and minimum. So what is the maximum? L and minus 0. Similarly, considering the second term, I have applied the maximum and minimum. So maximum value is L, substitute replacing x as well as replacing x in the lower limit, it will become 0. Okay, so sine 0 is 0, so the remaining is only L. Here also it is 0, so remaining is a square by 2 into L is the factor we have, which is equal to 1 according to the normalization condition. So now you can see that a square by 2 into L is equal to 1, or what is A? A is, what is A? Square root of 2 by L. So we can substitute for A now. So capital X become the wave function which depends only on small x, that is the dimension x. We'll get square root of 2 by L into sine nx pi by L into of x. Similarly, you can write for y, which would be square root of 2 by L sine ny pi by L of y. Ny means it is an integer corresponding to the y term. And similarly, z can be written as square root of 2 by L sine nz pi by L z. Okay, so now you have the wave function as, we have written it as a product of capital X, capital Y and capital Z. So now we can replace this. We can just write it down for capital X, capital Y and capital Z individually, and finally what you have is, from each term you have root of 2 by L. Okay, so root of 2 by L 3 times is appearing, so the cube is taken. So what you have is 8 by L cube whole raised to 1 by 2 and sine nx pi by L x into, so this is a term, sine of this much, and another term is sine of ny pi by L into y, then the last term is sine of nz pi by L of z. Okay, so we have also have the equation as kx square plus ky square plus kz square is equal to 2me by h cut square in the previous case. So substituting for kx and ky and kz, you can write it as nxy pi by L whole square plus ny pi by L whole square plus nz pi by L whole square, which is equal to 2me by h cut square. So from which you can see that all others are constants, so we can evaluate what is energy of the particle in the box. So energy is equal to, what is energy? Yeah, h cut square will come here divided by 2m, and pi square is available in all the 3 terms, so that is taken as a common factor, into remaining is nx square plus ny square plus nz square. This will come as suffix, and divided by L square is also a common factor, so we have taken it outside. So this is the expression for energy of particle in a box, and problems could be asked giving different values of integer values. You can find out what is the energy of the particle. So this is what I mentioned, whenever the electron hits on the boundary, it will get bounced back, and these are the representations of energy for different values of n. So here you can see that in the first case, where we are considering only x and y direction, when both are n is equal to 1 and y is equal to 1, you can see that the probability is like a Gaussian. This is called Gaussian, which means the maximum probability for finding the particle is displayed over here. It is like center line. Okay, but when you have more energy, if in the from the previous expression you can see that if nx value, ny value increases or nz value increases, naturally the energy of the particle will also increase. So for a higher value like nx is equal to 2, energy is greater than the previous case. So here you can see that now you can find out the particle in 2 positions. Okay, so as the integers in the value of integers increases, the value of energy is also increasing. So correspondingly, you will be able to find out the particles in many positions. Okay, there are more probability for finding the particles. So there are more energy possibilities are there. So initially, there was a single Gaussian. When the number of particles increase, the value of integer increases, there might be 2 positions. Similarly, as the number again increases, there might be 4 Gaussians. So similarly, as we increase the number of integers, the corresponding energy value also increases and more number of Gaussians will be there. Okay, so this is the inference from the particle in a box. We won't be able to pinpoint where the electron is exactly. This is the case for an electron in a hydrogen atom also, where you have only one particle, one electron inside the atom. So we are not able to pinpoint where it is, but if you can find out the energy, you will be getting what would be the probable position of the wave function. Similarly, the probability is given, 2 possibilities are there or 4 possibilities are there Remaining number of possibilities are there for finding the a particle inside a box. Okay, so that all depends upon the energy of the particle. So if it is highly energetic, like if it is a highly energetic person is there inside the room, what will he do? He'll be running around here and there. If it is a very idle person, he would prefer to sit somewhere alone, isn't it? If it is കുറച്ചും കൂടി energetic ആണെങ്കിൽ കുറച്ചും കൂടി ഒരു moving ഉണ്ടാവും. So we can find it out at two positions. And so as the energy increases, what the particle will be moving around will increase. So that is what is mentioned using particle in a box. Okay, so that ends this chapter on quantum mechanics. Thank you.